안녕하세요. I'm Jonathan Aldrich. I'm a professor in the Software and Societal Systems Department, part of the School of Computer Science at Carnegie Mellon University. I'd like to thank the Never Connect Foundation for inviting me to give this talk at SEF2022. Today I'd like to talk about how we can inspire the next generation of computer scientists. I'd like to start with a little bit about my story, what inspired me to start learning computer science. Like many computer scientists, I've always been a creator. I've been interested in building things. This is not a picture of me as a child. This is me with my child. You know, I was building a model with her of the rocket that went to the moon and all the different stages and so on. I like to see how things work, right? And I think I naturally became interested in how computer programs work. What's great about software is that as a building material, it's infinitely flexible. If you can imagine something, it's likely that you can create it. This theme kind of grew with me over my career. To write software, you provide instructions to the computer in a programming language. And so the programming language provides the building material of software. At first, I tried a very simple language. At home, we had an Apple IIc computer, and I used a very simple language called BASIC that was provided on the Apple IIc. Using this, I could create simple programs for the club that I had with my friends, keep track of all our stuff, show nice things on the screen. Very simple, but playing around, right, building things. Later in school, I learned a language that had more structure, Pascal. And I learned, that Pascal has sets and if statements and functions and all this structure, right, that really could let you build more professional things and build complicated things and rich things out of simple things. Later on, I learned about object-oriented programming and eventually the Smalltalk language, which is just an incredibly beautiful language. I experienced that at my first internship in industry. And in Smalltalk, you can take a set of simulation objects, for example, and simulate the world by having each of one of those objects do an action, take a step in a simulation. Today, my fascination with language continues, except I invent languages of my own. I'm trying to develop languages that have new kinds of type state. One such language is Plaid, and it has a type state that allows you to, for example, model a caterpillar and then transform that object into a butterfly, which has new information and new behaviors and so on. So this idea of expressiveness and the way that we express software through languages has always been a personal inspiration for me. Let me connect this with something that might relate to something your students are studying. We've created a language called Penrose, which is a language for visualizing mathematics. And so if a high school student might study geometry, and in geometry you have things like points, P, Q, R, and S. You might have things like line segments. Here, there might be a segment from P to Q and a segment from P to R. So we have a language called Substance, which captures the mathematical substance of an idea. Here we're describing geometry constructs in this program. So in addition to points and lines, we can talk about the midpoint of a line segment. We can talk about angles between Q, P, and R. We can bisect those angles and produce a ray that's at the bisection. We can produce triangles, and so on. Now this is math, but what's fun about geometry is that it's visual. You can create diagrams and shapes, and the intuition for geometry comes from manipulating these figures. And so we have a second language style that will actually take these commands in the Penrose substance language and turn them into diagrams. So a point in the substance language will become a point in the diagram. A line segment will become a line between the 2 points. And with a midpoint, then we create a midpoint, but it's constrained to be in the middle of the line that is the midpoint of. And so with the style language, Penrose will then be able to produce automatically a diagram that shows the triangle, the line segments, the angles bisecting things, and so on. And if we want to show several, we can show several different instances of this with, perhaps an isosceles triangle or different forms, right? But we can also explore different kinds of geometries. So a single set of mathematical ideas could be visualized in different ways. What if we're on the surface of the Earth? Then a line actually curves around the sphere of the Earth, and we have actually a different style for visualizing geometry in spherical dimensions. You can also get hyperbolic geometry using a different style file. So this gives you a little of an idea, right? We have a language for capturing mathematics, and we have a language for, I didn't show you the language for visualizing it, but that also, that's what provides the flexibility to visualize the same mathematical ideas all in different ways. So languages is where I do my research. I teach from some classes in languages, but I also teach classes in software engineering. And I'd like to talk a little bit about that because that's an idea that's important for programmers, for people who are learning computer science. Software engineering is really all about how to build software effectively at scale, right? When we first learn to program, we write small programs, but eventually we want to write more significant things. We want to scale up the programs that we write. And so one example of a software engineering technique is software architecture. Software architecture at its most basic level is how you divide a large software system into parts. So for example, consider a compiler. A compiler is a program that takes the program you write and transforms it into machine code so that the computer can run it. Compilers typically have 3 or more parts, but 3 of the critical parts are a scanner, which reads the program text that you write, 1 word or 1 symbol at a time, a parser, which takes that stream of symbols or words and organizes them into a data structure that reflects the structure of the program, and then the code generator, which takes that data structure and outputs machine code. So if you understand the structure of this compiler as being made up of those 3 parts, then you can understand how to build it better. And moreover, this architecture is important because we can have different teams of people working on different parts of the program. I can work on the scanner while you work on the parser, and one of our friends works on the code generator. And by working all 3 at once, we can get more done. And we can do that as long as we understand the connections between those pieces of the compiler. Furthermore, we can test the different parts of the compiler separately. I developed a language that had a more interesting scanner than most languages, and it was tricky to debug because it was more complicated. But by isolating it, I could test that scanner independently of the rest of the language and get it to be right. So testing the little pieces of a software system can be easier and more effective for many purposes than testing the whole program. You do have to do both, but you can find those bugs faster by testing individually. We can also make improvements to different parts of the program independently, right? So if someone wants to develop more optimized code in the code generator and someone else works on making the parser faster, they can work independently. So these are all important ideas about how to scale up from someone developing a small piece of software all by themselves to a team of people building larger software systems. Now, students can't always build large systems in their classes because there isn't time. But we can talk with them about design concepts, architecture, and modularity so that as they grow, they have those ideas and they can more effectively deal with large-scale systems when it's time to do so. Another thing that we've done in some of our classes is have students contribute to larger projects. For example, find an open source software project. Find a bug or a feature request, something small, something the right size for a student, and have them go and implement a fix for the bug, an enhancement, and make a pull request, and get the team to incorporate that idea into their software. So that's a way where students can do a small piece of programming, but have an impact on a larger system, and start to understand what it is to work in this scale, at a larger scale. Another important software engineering idea is the idea of analysis. My students here at Jasmine worked a lot on analysis. Analysis is studying software as well as software development processes to identify and address problems, to make the software better, and also to make the process by which we develop that software better. So one thing Sierra did was she studied program analysis, and she went during an internship and applied some ideas from her program analysis at eBay, the retailing site. She integrated find bugs into eBay's process to find bugs and in general improve their software. So they made a number of improvements based on this. One example was database queries, where the front end of the program was asking the database for information, but then it wasn't using it. And so this placed a load on the servers, on the database servers, that really was not necessary. So FindBugs could find some of those unused query information, and then by removing those queries, we could save eBay a lot of load on their servers. So Sierra moved on. She graduated, and now she analyzes engineering processes at Google. And she still publishes research on software engineering. In fact, there was a recent paper she wrote on predicting software developers' productivity. What was interesting is some of the major factors that her team identified were actually non-technical. Things like, are you enthusiastic about your job? Do your peers support the new ideas that you want to pursue? Do you get useful feedback from your manager on job performance? What kind of variety do you have in terms of the tasks that you do? And here's one that's kind of ironic, the ability to work remotely when you need to. Interestingly, this paper was from 2019, and we all worked a lot remotely shortly after the paper was published. Now, these are interesting for kind of understanding how to make people more productive on the job, but they're also interesting for teaching, because a lot of these ideas can also make students learn more effectively. The equivalent of job enthusiasm is communicating enthusiasm for the subject, right? Getting students interested in learning about computing. Building an environment in your classroom where peers support each other, right? Working in pairs, helping each other solve problems. Of course, our job as teachers is to provide good feedback to students about how they're doing, and they can learn faster if we give them feedback on that. Task variety, obviously students like to do different kinds of things. Working remotely is maybe something we've all done too much of recently, but certainly having some flexibility can also be a good thing. Let me talk about some tips for teaching that I use and that we use a lot at Carnegie Mellon. One of the most important ones is engaging students actively. As teachers, or perhaps parents who are teaching your kids, we often show our students things. But if we can engage their minds in a deeper way, they will learn better. Right? So one thing that I do every day that I teach, I bring a worksheet into the class with one or more exercises. I stop after presenting some ideas, and I have students fill them out in the middle of class. Then we go ahead and we talk about the answers before we go on. Let's illustrate. All of you teach something, right? Perhaps you teach your students, maybe your children, maybe you could teach something to your peers. Think about something that you would like to teach. I'll give you a moment to think about that. Okay, hopefully you have an idea of something you might want to teach to a friend or to a student or your children. Now, what is a question you could ask them about the topic? You've told them something about it. What's a question you could ask back to them to get them to think about it and see if they understand? Again, take a moment, think about it. All right, do you have your question? Okay, so we're doing this right now, right? If you were in my class, I'd have you write down that question. I'd have you share your answer with other people in our seminar here before we go on to the next slide. Okay, so this is a way that you can get students to think about what they're doing and reflect on it, and maybe put it into practice. Give them a little problem to solve, and they'll learn better. They'll remember what you said. Another idea that I think is very important in computer science is getting practice for fluency. Learning to program is a lot like learning a language. You have to practice a lot until you're fluent and can talk and communicate effectively. So what I find it's important is to have students practice the most basic concept many times. Of course, you don't want to be repetitive. You want to use that concept in different settings every time. But the idea is that as students practice, the basics become easy, and then students can build on them and use them in a very fluid way when they're learning higher level material. A third tip is frequent feedback. Right? Find ways to create opportunities to interact with your students, with your children, so that you can give them feedback. This is one of the big benefits of active learning in the classroom. There are more chances for you to find students, see what's going on, adapt your teaching to them, correct student misconceptions that might crop up. You can do this with them in your class. You can do it in office hours. Your teaching assistants can work with them if you're in a university setting. But also, having students use tools that give them feedback is great. One of the wonderful things about writing software is that you have a compiler, and the compiler gives you feedback. It tells you, is there an issue with this software that you're writing? But also, you can give students test cases, right, that their assignments must pass. Something that I've done very practically in this area is created a tool called SassYelf. In my classes in programming languages, I teach students to prove things, mathematical proofs about programming languages. Unfortunately, in a lot of times when we teach proofs, it's hard to give students feedback on them, and students might make mistakes and not even know that they're mistakes until they get their graded assignments back. But then maybe the opportunity to learn has been lost, right? Because they don't correct their mistakes afterwards. So if we have a tool that can check their proofs for them, that's what SassYelf does. And then students know when their proof is wrong, and they can fix it right there. Or they can go and call the teacher and ask the teacher, hey, what don't I understand about this? And so it creates an opportunity for them to learn and get that feedback, get it right away, learn when the opportunity is right there. I talked about inspiration earlier, and I'd like to share 3 stories of inspiration. The first was by someone I'll call Ivy, not her real name, because this is a story from very early in her computer science experience. I was a teaching assistant in graduate school, and in the class, the final project was building an exploration game. Ivy went well beyond the requirements and created a whole story where a knight rescues a princess and there's a celebration at the end. I don't have a screenshot, unfortunately, because this was 20 years ago, but I've created these minifigures for your imagination. So Ivy's project wasn't the most complex one in the class, but it did show enthusiasm and creativity and hard work. And I think that persistence, that excitement for computer science paid off. Today, Ivy is a partner group engineering manager at Microsoft. So she's done very well and has a leadership position in industry. I think that shows the trajectory from perhaps very simple programming, but a lot of passion and energy and excitement to doing great things in one's career later on. Second example is more close to home. This is my child, Seal. During the COVID-19 lockdown, Seal learned at home, like many students did. And in fact, Seal and my wife took a class from me learning computer science basics, just in our house. And the class project was building an app that expressed their interests. Now, Seal is a dancer, and Seal loves music, and Seal loves K-pop music. So, they created a create-your-own K-pop group app. I'm going to show you some screenshots. The real app actually has pictures of K-pop idols, so for copyright reasons, I'm replacing them with pictures of our kids dancing. My kids are my idols, so we'll go with that. But you can create your own K-pop group. You can say how many members. Is it a small team, a single act, or a big group? You can choose the different members for your team. You can choose a set, are we dancing in Times Square in New York? Are we dancing at home in the living room? And then it constructs your group for you, okay? Again, simple app, but it connects the thing that Seal is passionate about, dancing, K-pop music, with computing, and creates something they can show their friends and use. Third example is my wife, Becky. My wife, Becky, is a pianist, a piano professor, and a private piano teacher. She actually took my homeschool class and learned to program right along with my child, Seal. Now, a challenge for music teachers is teaching music notation to beginners. Music teachers mostly want to focus on the instrument, not teaching music reading, right? They want to play music with their students. So Becky wanted to build an app that would help her students learn to read music. Well, she got started with it, but it actually turned out to be too big for a class project. But when I took a sabbatical, a semester off from my teaching at Carnegie Mellon this past spring, we formed a team, and I worked with her to build the Noteful app to realize her vision. This was a great chance for me to practice the software engineering skills that I teach and actually build a piece of software. But it was also a great chance for her to find a way to use software to enhance the thing she was passionate about, right, which is teaching students music. And if you're interested, I'm hopeful that Noteful will come to app stores soon. So back to inspiring future computer scientists. As we teach, I think it's important to teach immediate skills, right? How to program the computer, how to use the computer, but also talk about scaling up, right? What are the enduring principles that they'll use? Things like software architecture, things like how to analyze software like my student Sierra did. Engage students in the classroom. So give them lots of practice, give them lots of feedback, interact with them, and encourage them to find ways to use computing to get to their interests, whether it's telling stories, whether it's teaching music, whether it's dance and music. Encourage your students to find the thing that inspires them. Thank you very much.